So hello again after lunch. So now it's easier, I think, to prove something. Okay, so let us continue with this approximate pattern matching business. So we still focus on the mismatches. So we are not going to do anything about the diversion with errors. So it's just pattern matching with k mismatches. So before we proceed, we need one tool which is interesting on its own. So it's approximating the number of mismatches. So now the setting is that you again get the pattern and the text, and for each position for each possible starting position, so for each alignment of the pattern and the text, you would like to approximate the number of mismatches. Okay, so that's a natural question to ask. I mean, maybe even more natural than finding occurrences with up to k mismatches. So that's the question. So for each I, you want to output this number di, which is at least 1 minus epsilon times the Hamming distance, and at most 1 plus epsilon times the Hamming distance. Okay, that's what we want to compute. So did you have an idea how to compute it over lunch? No? Okay, so it's not so easy. So let me give you some. Sorry? Yeah. But if you now you could do that, and if you have many mismatches, you should be able to tell something about the approximation guarantee. But it might be the case that you have only 7 mismatches for a particular alignment, and the chance of hitting those positions will be very, very low. So somehow you would like to sample, but the space from which you sample should be smaller. Should be not all the positions in the pattern, but somehow you should filter. Yeah? Okay, but this sampling it's a good idea. So our algorithm will be randomized. So the algorithms that we have seen before were all deterministic, which is good, I guess, because some people don't believe in randomness. Okay, but this will be randomized. So let me give you some history. So the first algorithm for this question, so this will be very efficient. It will be almost linear time. So m with some logarithmic factors, maybe 2, maybe 3, we will see. And of course, the complexity will depend on epsilon, on this approximation guarantee that we would like. You can see immediately that it needs to depend on epsilon, because if you set your epsilon to be very small, 1 over m, you will get what? The exact answer, right? And we have seen that for the exact answer, probably you cannot go below n times root m, assuming this matrix multiplication conjecture that we were not able to state precisely. Yeah? I know. Yeah, I will change in a minute. You mean the one-sided? You want one-sided? I will change in 1 minute to one-sided. Yeah, I mean, you're right, but in some of the papers about that, they start with this formulation. I don't know why, but I wanted to be consistent. Okay, so this is what we want to solve. So the first algorithm, the first efficient algorithm was given by Karloff like 20 years ago. And the complexity was n divided by epsilon squared. So the dependency on epsilon was quadratic. Okay? And he had some log factors, 2 or 3. And it was not very complicated, but not so straightforward. And then 3 or 4 years, I'm not sure exactly, there was a paper by Kopelowicz and Porat, and they managed to decrease the complexity to n over epsilon. So the dependency on epsilon was just linear. And that was kind of surprising for a lot of reasons, mostly because of some connections to streaming algorithms, where you can actually show that you need quadratic dependency. I mean, I would have to go more into that, but there was some reason to believe that maybe this quadratic dependency was the right answer. Okay, but they were able to kind of break it. But the algorithm, I would not be able to present the algorithm during 1 hour. Fortunately, this year there was this conference SOSA, Simplicity an algorithm, and they gave a very simple algorithm for the same problem. So it'll be on 1 slide. I will show it to you on 1 slide. It's the same authors, Kopelowicz and Porat. So let me show you the algorithm. Okay. Again, we will use FFT. So we will use convolution a few times. How many times? Well, our complexity will be n over epsilon times some logs. So you can guess the number of FFTs that we are going to use will be 1 over epsilon, maybe times some logs. So we will repeat the following procedure. logarithmic number of times. As usually in randomized algorithm, okay, maybe I don't know if you know that. Do you know the difference between Monte Carlo and Las Vegas randomization? Who have seen something like that? Some people, but not everyone. So let me just define it. So when you talk about randomization, there are two notions of randomized algorithm. One of them is that the answer might be not correct, but the chance that the answer is not correct is very small. Okay? And that's called Monte Carlo. So you can bound the probability of receiving the correct answer. And you will say that with probability at least 0.9999, my answer will be correct. And you do that by adjusting some parameters in the algorithm. And the better the guarantee, the slower the algorithm. Okay, so it's Monte Carlo. And the other notion is Las Vegas algorithm. So in Las Vegas algorithm, the answer is always correct. So you always get the correct answer, but the running time depends on the random choices of your algorithm. Okay, you do some random choices, and depending on whether you are lucky or not, your algorithm might be slower or faster. Okay, so here we talk about Monte Carlo randomization. So the answer might be incorrect, but we'll be able to bound the probability of receiving the incorrect answer. And usually in those Monte Carlo algorithms, you repeat something a few times to bound the probability of receiving the incorrect answer. Okay, so you repeat the same experiment 10 times, and somehow you adjust the parameters so that the more times you repeat, the smaller is the probability of receiving the wrong answer. Because to get the wrong answer, all your experiments must have failed. Okay, so here also we repeat log n times, logarithmic number of times, the following experiment. So we choose a random function. So we choose a hash function, which is completely random. So it should map your alphabet to a smaller alphabet. Okay? So you start with alphabet of size, you don't know, could be very large. And you map it, you project it into an alphabet of size 2 over epsilon. Okay? So it's much smaller. Think about epsilon being some small constant. Okay? And you do it randomly. So each character is mapped to a random character from the small alphabet. Okay, so that's the first step.
If the sigma is too big, right?
Sorry?
We do it only if the sigma is
Yeah, but if sigma is small, we can compute the exact answer in times sigma times n. We had this first FFT. So the interesting case is when sigma is large. Because when sigma is small, you can... but you are right. If sigma is smaller than 2 over epsilon, that would be stupid. You would just run this basic FFT. Okay? So that's the first step. So now you have this random function h. It operates on characters. You can extend to strings. Yeah? So now you can take a string and apply this function h to every character in your string. And that I will denote by h of p. So that's the result of applying this function h to each character, to each position in your pattern. Okay?
We know the value of the function on the alphabet, and what is the value of the concatenation?
You just take the value for each character in the concatenation, and you concatenate the results. You apply it for each position, and then that's what you get. Okay? Make sense? So now you do that for the pattern, and you also do that for the text, for each position in the text. You apply this function h. Okay? So now you have constructed two new strings, the projection of the pattern and the projection of the text. And now you compute the score, the number of mismatches, for each position in this new text. Yeah? So for each position in the new text, you count the mismatches between the corresponding fragment of this new text and this new pattern. Okay? So it's a very simple algorithm. You take your pattern and your text, you apply this random function h to each character in the alphabet, but it's the same function being applied to both the pattern and the text. And if a given character c appears many times in the pattern, you apply the same function. So for instance, you could replace character a by number 7, right? And to do that consistently, for all occurrences of this character. Yeah, this is important. And then you get a new instance of pattern matching, and you compute the number of mismatches for this new instance. Okay, so that's the algorithm.
So capital H is the number of...
That's the Hamming distance, so that's the number of mismatches. Okay, and xi is the number of mismatches for the alignment starting at position I in this text. Okay, so that's the experiment that we do. So the complexity is easy to analyze. I mean, the way I wrote it, it might be not completely clear how to do it efficiently, because I said that I compute something for each I, and that might be slow, right? But what you really do in step 2 is that you solve an instance of pattern matching with mismatches on the new text and new pattern. So you just do that using this first non-naive algorithm, which works in times size of the alphabet times complexity of FFT, right? That's what we started with. But now the size of the alphabet is much smaller because we project sigma to something of size 2 over epsilon. Okay, so when you look at this new pattern and new text, those are strings over alphabet of size 2 over sigma. So to solve pattern matching with mismatches for such strings, you need 2 over epsilon invocations of FFT, right? Each of them takes you time, well, n log m. Yeah, n log m, because again, you cut into fragments of length 2m and you apply FFT for each of those fragments separately. Otherwise, it will be n log n. Yeah, and this whole procedure needs to be repeated log n times to amplify the probability. Okay, so the complexity is clear, right? Make sense? Now we need to analyze the correctness. I mean, what's the probability that we'll calculate an incorrect answer? So now let's look at some position, some alignment I, and say that the real Hamming distance between the corresponding fragment of the text and the pattern is d, small d. So that's the real answer that we would like to obtain. Okay. And now let's calculate d minus xi. So how much we could differ? What's the difference between the answer and what we return? Okay. So we want to bound this quantity. Yeah. What's the difference? Okay. So what could be the reason for our answer to be different? Well, it could have happened that, so again, we count mismatches. We count mismatches, right? So a mismatch is when you have character A here and character B there, and they are different, then you should add 1 to your result, okay? But now it could happen that in your random function, A and B are projected to the same character in the small alphabet, right? So you could have a mismatch, which kind of disappears because of that, okay? Okay, but what's the probability of that? Well, so you have this character A and B, that's the mismatch, and the value of function of h at A is something. Let's say that it's fixed already. And with B, you would have to hit the same value in this new alphabet. But what's the probability of that? Well, you have 2 over epsilon possibilities, right? So each mismatch might disappear with probability at most epsilon over 2. Okay? Make sense? Okay, so that's for this expected value. So that's how much we could differ. Okay. But now it only tells us something. What's our goal now? So this is just for a single position, for single I, and it only tells us something about the expectation, which is a very weak condition. Right? We would like to have some better bound on what's the chance that our answer will be very, very much different. Mm-hmm.
So here, by surviving a mismatch, you mean that the mismatch actually becomes a match? Right?
Yes. Instead of contributing +1 to the answer at the corresponding alignment, it no longer contributes +1. Okay, so this expected value, we are good with that? Okay, so now what we have to do is to use some inequality. Here it's just Markov's inequality, because we can bound the expectation. So we can, some Markov inequality allows us to bound the chance that we'll deviate too much from the expectation. Okay? Okay, so if you plug in the Markov inequality, then you will get that the probability that your xi is smaller than 1 minus epsilon times d times the real answer is at most 1 over 2. That's just by plugging in the. Yeah, if you know Markov's inequality. So if you plug it in, you just get this answer. I can I'm not sure if it makes sense if to kind of. Okay, so the chance that the particular xi is too much off in our experiment is at most 1 over 2. Okay, so what do we do now? Well, we repeat the experiment many times, right? And for each xi, in every experiment, the chance that xi is too small is less than 1 over 2. Yeah, so we repeat many times and we return the max. So for the maximum value to be too small, all experiments must fail because we return the maximum. Okay? So we repeat the same experiment again and again, and we return the maximum. So if one of them returns the good answer, then we'll get the good answer. So the only remaining case is that all of them return too few mismatches. But for each of them, the chance of that is at most 1 over 2, independently for each of them. Okay?
So now we are only bounding from one direction.
Yeah, just for one direction. But I will discuss, yeah, now it's only one direction. And it's, okay, this part is it's okay? Can you kind of see what's the reason here? Who can kind of believe that this is true? Good, okay, so if you believe, that's enough. Okay, so that's for one position I. We get that by returning the maximum from those experiments, the chance of getting the correct result is at least 1 minus n to minus c. Yeah, because the chance of all of them failing is 1 over 2 to c times log n. Okay? So by adjusting this c, this constant c, we can get the probability for a single position I to be smaller and smaller. And in particular, we can choose our c to be, let's say, 5. And then the chance that we get at least one position I for which the alignment is incorrectly approximated is small enough. Okay? Because here I focus on one I. But by choosing c to be sufficiently large, I mean, I get that for all of them, I will get the correct answer with a good probability. Okay, so this is the whole algorithm. So it's a very simple idea, very beautiful idea, I would say. So one page. I mean, here I didn't write all the calculations, but they are easy. Okay, but now the question is, I bound the error only from one side here, right? I only bound the number of, what's the chance that I will get too few mismatches? But can I get more mismatches? No. Yeah, so there is no need to bound from the other direction. So in fact, my definition on the previous slide was maybe a bit, yeah, I will not say what it should be maybe just from one direction, yeah? Just the left inequality is interesting, and the upper would be that I get at most the answer, at most number of mismatches. But in fact, as Karol pointed out, the usual definition is in the other direction, that we want our number of mismatches to be not too large. Right? Usually we would like to report something which is at least the number of mismatches, and at most number of mismatches times 1.5. We will see why we want to do the other direction in applications. But probably you can see that you can go from one version to the other version very easily. Do you see how? So if we can approximate from one side, you just multiply the result. Right? If something is between 1 minus epsilon times the answer, at most the answer, you just divide your answer by 1 minus epsilon, yeah? And then you get the approximation from the other side. So it doesn't really matter. Yeah. And if you could approximate from both sides, you could also multiply by something, and you would get one-sided. So here it doesn't really matter that much. Okay. Okay, so that's the algorithm. Yeah, so we will use this version. The answer is at least the Hamming distance, and at most 1 plus epsilon times Hamming distance for every position I with some good probability. Okay, and the time to find this approximation was only n over epsilon times 2 logs. And from now on, I will keep adding logs one by one. So I will not write them down explicitly because then it's ugly. Okay, so it's essentially n over epsilon. Questions? Yes, epsilon is how it affects the running time, and it also tells you how good is the approximation ratio that you will get. So you could set, I don't know, 0.01, and that's probably quite good. And C is the error probability. So C doesn't have to be that large, because when n is large, then you will get small chance anyway. For C equal to probably 3. I mean, C doesn't yeah, that doesn't. Yeah. Okay. So, any questions about this part? No? Okay, good. So, it is not known whether you can improve a lot. This depends on epsilon. But for some time, people couldn't improve the quadratic dependency, so I guess it's a bit too much to ask to improve the linear. So I'm not aware of any.
For string, so do you mean that in the string model they put lower bound? Like,
there is something about space lower bound, which also turns out to be quadratic in epsilon, but it's a different game. But that was, I guess, that was indication, not like a solid argument, but an indication that. So there is something for sketching where they can prove that you need your sketch must have at least quadratic dependency on epsilon size-wise. I think by Woodruff, but I'm not sure. Okay. So now let me show you some ideas. I will not show you the whole algorithm because there are many components. I will just give you some general flavor how it works. So there is one high-level kind of idea which also shows up in other algorithms. So I want to show it to you. So it's now I'll try to use this multiplicative approximation to solve pattern matching with k mismatches. And now instead of n times k that we have seen before lunch, we will have n times k divided by root m. Plus n. I have to add plus n because otherwise it would be weird not to read the whole input. I mean, that's not a reason, but it would be weird. Okay? So for small values of k, we get a very good running time, linear running time, up to root m. And then you get this curve of complexities. Okay? So we would like to do that. So now what's the high-level idea? So I didn't show you anything about the exact pattern matching, but it's also used very heavily in all other exact problems. So the high-level idea is that you look at your pattern. You look at your pattern very carefully, and you have essentially two cases. So either the pattern is repetitive in some sense. So for instance, it looks like AAA. So it's a very boring pattern. So it has a lot of combinatorial structure to it. And when there is this combinatorial structure, you can kind of exploit the structure to accelerate your algorithm. If your pattern is AAA, then it's not so difficult to find it in your text, right? Of course, this is a stupid example because it might be more complicated. Yeah. So in exact problems, this notion of being regular is usually the periodicity, the notion of periodicity. So a string is periodic when the character at position I is the same as the character at position I plus L. And then we say that L is the period of your string. Yeah, so you have those blocks of length L, and they repeat again and again and again. And at the very end, you might have an incomplete block. Okay, so that's the usual periodicity. And it turns out that if this value of L, the length of the period is small, then it has some structure, and you can try to exploit this structure. Okay, so that's what it means for exact. Here it will be a bit different, but. Okay, and the other possibility is that the pattern is not regular, and in such case, its structure it's so complicated that you don't kind of need to look at all characters of your pattern to eliminate many possible alignments. So just so many things happen in your pattern, so that you can kind of forget about most of the characters in the pattern, and the remaining characters will introduce so many mismatches already that you don't have to kind of look at the other. Characters, right? Because you need, as soon as you have found k mismatches, you don't really care whether it's k, 2k, 3k. Yeah, as soon as you have found k mismatches, you are done. You don't have to calculate the number exactly. So you can hope to kind of remove some of the characters in the pattern, do something with the remaining ones. There are fewer of them now, so it's easier. And then it might allow you to eliminate many possible alignments. And for the remaining alignments, you just spend more time because there are fewer of them. Okay, so that's the high-level idea. Make sense? Some sense? I mean, it's very general, but I will show you more concrete example. Okay, so for exact pattern matching, this notion of being regular or not is just this periodicity. So you look at, essentially, you look at patterns which are periodic, meaning that the period is at most half of the length, and aperiodic, non-periodic, where the period is longer. And you design a separate algorithm for one case and for the other case, and then you carefully combine them, and you hope that it's enough to solve the problem. So here we will need a slightly different notion. So again, period of string S is number I, such that character at position j is the same as the character at position j plus I. Or in other words, if you take the first n minus I characters and the last n minus I characters plus 1, you get the same string. Okay? Can you see that this is the same? Yeah? Maybe I should show it. Yeah, so you look at your string. Mm-hmm. Sorry, again, I forgot. So this is your string. So complicated now. Oh, this is good, huh? So this is your I. You have those blocks of length I, and then this possibly incomplete block. Yeah, and then when you take this, yeah, and you kind of move it here, it's the same string. Okay, so that's the usual notion of periodicity. And I will not use it, but I will show you just one lemma. If you read any paper on periods, that they use this lemma. It's called, well, D periodicity lemma. So D period is the shortest, the smallest non-zero value of I, because you could have many periods. If you think about the string AAAA, the periods are 1, 2, 3, up to the length, right? So you want the shortest, the smallest one. And there's this easy lemma that when you have two periods, P and Q, of the same string, and if P plus Q is at most n, then actually the greatest common divisor of P and Q is also a period. Okay, so when you look at, you have your string, it could have many different periods. If you look at all periods which are not too large, they actually have a very nice structure. There are multiples of the period, of the shortest period. That's what you get from this lemma, right? Because when you take two periods, each of them is at most half of n, then this the condition of the lemma applies, and the greatest common divisor is also a period. Okay, so when you take all periods which are at most n over 2, the greatest common divisor of any two of them is also a period. So the greatest common divisor of all of them is also a period, and that's actually the smallest period. Yeah, so you have all those periods, but the first half is just very regular. So there is a nice structure, and the others also have similar properties, but you have to work a little bit with this lemma. Okay. I will not use it, but it's good to know that something like that exists because it's used in those exact problems. Okay, but we don't want exact, we want approximate. So what do? You forget about this slide and you introduce, not completely, but for the next 10 minutes. And you introduce a version where you need to put the Hamming distance in the definition somehow, right? Because now it's not the exact, it's a Hamming distance at most x. Yeah, so we have this notion of x period. So when you look at the previous, I should have put it on the same slide, yeah? So when you look at this definition of period and x period, you can see that they're almost identical, except that instead of equality, my condition is that the Hamming distance should be at most x. So 0 period is just period in the traditional sense. Yeah? So I want to take the first n minus I characters and the last n minus I characters, and the Hamming distance between those two strings should be at most x. That's my notion of x period. Okay, so it's a natural generalization of period. Okay, so I have this definition. But we want a lemma, not a definition. So what you can do here. So let's say that you have your pattern, and let's look at its 2x period. So again, you could have many different 2x periods, right? You choose an of them. And well, here you want the smallest one, the smallest I, and that's the x period. And let's say that it's L. Okay, so you have your pattern, and the smallest I, such as this condition holds for 2x is L. Then I claim.
But x is x
uh,
period.
yeah, I'll be using different values of x, so that's maybe a little bit confusing. So by 2x period, I mean that the Hamming distance is at most 2x. Okay, you have to substitute in the definition 2x instead of x.
Okay.
That's the only. Yeah, maybe I should have used y and x, but okay. Do you see what? Okay, so now let's think about occurrences of the pattern in the text. So there are many of them, and we would like to somehow say that because this 2x period of the pattern is at least L, and think about L being a large value, then we would like to say that the pattern cannot occur too often. Again, we have pattern matching with mismatches, right? So we look at occurrences with k mismatches. Yeah, so we claim that if the 2x period of the pattern is L, then two occurrences of the pattern where we look for occurrences with x mismatches must be at least L positions apart. Okay, well, okay, so that's the formulation, and it's good to think about the exact version with no mismatches. So if I have two occurrences of the pattern in the text, right, with no mismatches, and the difference in the starting positions is z, okay, then it means that z is a period of the pattern. Okay, do you see that? Because I have my text, I have one occurrence and some other occurrence, and this is z, yeah? But then it means that in the pattern, the character at position 1 is the same as at the position 1 plus z, and so on and so forth. Right? So for the exact version, if I have two occurrences of the pattern at offset z, then z is a period. Make sense? This part? But when you think about this notion of x periodicity, it's exactly the same situation. I have two occurrences of the pattern with x mismatches here and there. Okay. So now I claim that the Hamming distance between this and that is at most 2x. Why? Because when you look at this occurrence, it has at most x mismatches with the text. This occurrence also has at most x mismatches with the text. So now look at position here. Yeah. If it doesn't contribute to a mismatch for any of those two occurrences, then it's the same as the character in the text, so it's a match. But it could also happen that this letter in one of the occurrences contributes to a mismatch with the text. And then it might or might not contribute to a mismatch between those two occurrences, right? So you have, make sense what I'm trying to say? So if I have to have a mismatch here, I need to have a mismatch at least one of those two occurrences. Otherwise, they are the same as the character in the text, so they are equal to each other. Okay? Who can see what I want to mean? Okay. Well, so we have some structural insights. So if intuitively, if your value of L is large, you get fewer and fewer occurrences. Right? That's what this lemma is saying. This very simple lemma is saying. It means that if your pattern has the property that its 2x period is large, and you can expect x to be k, because in the end we look for occurrences with k mismatches, but it will change on the next slide. You will see why. But think about x being roughly k, okay? Because we are looking for occurrences with k mismatches. So then you know that you will, in the end, you will get few occurrences at the end of the algorithm. That's what this lemma is telling you. If you are lucky and your pattern is non-repetitive in this sense, then you can't have too many occurrences. Okay, but that doesn't really help you in your situation, because you have to find those occurrences. This only tells you that in the end you will have very few of them. But that's not so helpful. I mean, you need some help in finding them. Okay, that's one problem. And the other problem is that the 2x period of your pattern might be small, and then this doesn't give you anything at all. Okay, but now so there are at least two major issues, and actually there is a third issue so you want to distinguish between the pattern being regular and not regular, and then you want to do two different things depending on that. So you need to calculate the x period of the pattern. Because so we want to say that our pattern is regular if the x period for some value of x that I will show you soon is small. But then you need to calculate this x period, right? You need to compute what's the smallest I, such that after shifting the pattern by I positions, you get few mismatches. But it means that you have to run pattern matching with mismatches on the pattern, right? If you want to do it from the definition. So we have reduced the problem to itself, which is not so useful, right? Okay, so here is the first trick that I want to show you. So actually, you can plug in this approximate counting of mismatches. So I'm saying that look at your pattern, and instead of finding its 2x, instead of finding its x period exactly, we will kind of approximate it. So we won't know for sure how large it is, but we will get some bound on how large it is. Okay, so we won't know exactly whether the pattern is really not regular or whether it is regular, but there will be some bound on how it looks like. Okay, so I'm saying the following: just run your this 1 plus epsilon approximation algorithm with the value of epsilon set to 2. So we find two approximations for each alignment of the pattern with itself. Yeah, that's your pattern, and you shift the other copy of the pattern by I, and you compute the mismatches. You approximate it within a factor of 2. Okay?
So what is the new pattern?
Sorry?
What is the new pattern which you run, on which you run this? You have a pattern?
Just the pattern. You take the pattern, and to compute this x period, you have to take the pattern, you have to find the smallest I, such that when you align the pattern with itself at offset I, you get very few mismatches. That's the notion of x period. You would like to take the pattern and take another copy of the pattern, align it in such a way, and then you count mismatches, and you would like to have at most x mismatches here. That's the notion of x period. We say that I is an x period if this holds, and we want to find the smallest I. So someone gives you the value of x, and your goal is to find the smallest, to shift the pattern by as few positions as possible, so that it matches itself. Okay? So I'm saying, instead of counting those mismatches here exactly, use two approximation algorithms.
I don't understand how to use this algorithm for this task.
So what this approximation algorithm does, it receives a text and a pattern. And then for
Here is the text and what is the pattern?
this is the pattern and this is the text.
So the text and the pattern are of the same length.
Yes. So here, maybe I see what you are maybe worried that this kind of sticks out of the text. Is this what worries you? Just put don't care characters, like question marks. They don't introduce any mismatches at all. If you think about how this algorithm that we had on the first slide works, it can also deal with don't cares in one of them. Okay, so append enough new characters to
It's slightly large. So text is slightly large.
so now it will be 2m. Now it will be 2m. If you put those additional don't care characters, it will be 2m. You have to verify that this algorithm from the first slide works with don't cares, but it does.
Just the H map these characters to the same characters.
Yeah.
And then you compute it for each alignment.
For each alignment I. Yeah.
Then you take the smallest one, which is
Yes. Yes. But now you are not really sure whether you have found the smallest I, because the number of mismatches that you count is you approximate it within a factor of 2. So you might have 11 mismatches, but your answer was 17. Not more than 22, right? But because it's a factor of 2 approximation. So now you are not really sure. But you get some constant factor approximation. Okay? So now the first claim, and maybe also the last claim, is that there are not many things you can be sure about in life, but here you can be sure that you'll be able to distinguish between the following two cases. So either the decay period of the pattern is at least k. So the k period is large. That's the first case. And the second case is that you can find an 8k period which is at most k. So it's a bit painful to read, yeah? But okay, that's the claim that we want to do. So we would like to say something about 4k period. So that we can't really do that, but we can say that either the 4k period is large, that's one case, and the other case you don't really know much about 4k period, but you can say that for sure 8k period is small. And this 4 and 8 comes from the fact that you approximate within a factor of 2. Yeah, in the definition of x period, x is how many mismatches you allow, right? But now you don't count the mismatches exactly. You might report too many of them, but not more than a factor of 2. Okay?
What does mean every for k period? Because that is only one?
I mean that the 4k period is I mean that when you think about periods, you can have many periods. Usually you think about the smallest period, the shortest period. So yeah, so in particular, the smallest one would have the property, but I wrote that, yeah. Okay, makes sense what we kind of want to have here? Okay, so here you just have to work through the definition. It's you have just to look at what's happening. And from these two approximations, you get that you will be able to distinguish between those two cases. I think you can kind of believe that you can distinguish between something. Yeah? Sorry? Why not? You map into 0, 1. It's, well, epsilon should be, yeah, I guess it should be smaller than 1, at most 1. I think 1 is fine. I think 1 is fine. If not, you could put something smaller, and it will give you even better ratio. Okay, I want to show you some ideas for the further parts. So here you can work through it maybe tomorrow during the problem solving session. And I think you can kind of believe that you can distinguish between some approximation notion of being regular and not from this. Okay, do you see kind of what's the idea here? Yeah. Okay. So now you have those two cases. You can distinguish between those two situations. So you need to design a separate algorithm for both of them. Because you don't know. I mean, you get your pattern and you don't really know which of those two cases will apply. So you need to.
Though I really need to distinguish them, can't I just run the first part and the second part and some of them will work? Why do I need to distinguish?
You could, but you would have to terminate the. So you have two parallel things, and the running time will depend on some parameter. So you would have to terminate after some time. I think you could do that. But still, to prove that this is correct, you need to work through those two cases. But you are right. You could run two of them in parallel and just terminate when they take too much time. Okay. So let's look at the first case, when we know that the 4k period of the pattern is large. Okay? So you know when you look at all possible occurrences with pattern of the pattern with 2k mismatches, they're kind of not too close to each other. They are at distance at least L, which is at least k. Okay, so this is what you get from in this first case. So 4k period is at least k, and I will use L to denote its exact value. Okay, so what does it mean then? It means that you have at most m over k occurrences with 2k mismatches. Because again, we had this very simple observation that if you look at all occurrences of a pattern with x mismatches, and the 2x period is L, then those occurrences are scattered by at least L positions. Okay, so if your 4k period is large, then it means that the number of occurrences with 2k mismatches is at most m over L, in fact, but L is at least k. Okay, so you know that the number of possible occurrences with 2k mismatches is small. It also means that you have at most that many occurrences with k mismatches. Yeah, because when you allow more mismatches, you will only get more occurrences. So you know that what you are looking for. I mean, there are very few positions that you are interested in, but how to find them? So I claim that it's not very difficult. You can again use this approximation algorithm with epsilon set to 1, but now you just take your text and your pattern. Okay, and you run this algorithm from the first slide on your text and your pattern. So what you will obtain is a 2 approximation of the number of mismatches for each position. Okay. And now it means that when this 2 approximation gives you 2k, then you cannot be sure whether the answer is 2k, 2k plus 1, or maybe 4k. You don't know because it's 2 approximation, right? But still, you can filter the starting positions that have more than 2k mismatches, yeah, because you approximate within a factor of 2, and you are looking. In the end, you want the occurrences with at most k mismatches. So if what you get from the approximation is 2k plus 1, you know that the real answer is at least k. Yeah, because if the real answer is at most k, then the approximation is at most 2k. Yeah, so if the approximation gives you more than 2k, you know that it's not a good starting position. Okay? So you filter out those starting positions where the approximated value is too large. That's the first step. Okay. And then from the first observation, we get that the remaining positions, there are very few remaining positions. Yeah. Because the remaining positions are occurrences with at most 2k mismatches. Yeah. But the 4k period is large, so then there are few of them. There are only m over k of them. Okay, makes some sense? So I think I'm losing you slowly. But, okay, anyway, use this approximation to filter out some of the positions. And then you show that there are only m over k, the remaining ones. And then you can afford to use this very slow, I called it the kangaroo jumps. Yeah, because you have only m over k candidates. So you can verify each of them in O of k time by just computing one by one the number of mismatches. So for the second step, you only spend O of k times for each of those remaining possibilities. But there are only m over k of them, so you spend O of m in the second step, okay, because of this filtering. And that's quite a usual trick. Also in the exact version, you somehow try to filter out the possibilities, and then you say that, oh, okay, now maybe I can't be really sure whether what I have is the correct answer or not, like an occurrence, but I just verify naively. And because there are very few of them, then it sums up to something good. And because I can bound this filtering, then it works. Okay, so then this part works in O of m. And let me just spend 5 more minutes on showing you the second case. So the second case uses a different method. So recall that the second case was that the 8k period is small. Yeah, so the first case was that the 4k period was large, and the other was that the 8k period is small. So the pattern is kind of repetitive in some sense, under this weird notion of being X periodic. Okay? So now when you have to kind of get a good mental picture of what this notion means, and a good way of doing that is to first introduce this notion of so you take your pattern, so S will be the pattern later. You take your pattern and you look at character at position I plus L, I plus 2L, I plus 3L, and so on and so forth. So you extract an arithmetical progression from your pattern, from your string in general, and you do that for every possible offset. So you do that for I equal 1, 2, 3, 4, 5, up to L. Okay, so you extract this one arithmetical progression with progress L, then another one, and so on and so forth. Okay, and then you write them down one by one. So first you write this progression starting at 1, then you write down the progression starting at 2, and so on and so forth. So you kind of reshuffle your pattern. Okay, and this S with lower subscript L is just what you obtain. So all those progressions written down one by one. Okay, so just a way to reshuffle your string. And now you think about this string, this reshuffled string, and you think about the number of runs inside. So a run is like in run length encoding that you probably know, right? So how many maximal fragments consisting of the same letter you have? Yeah? So you might have A, and that's one run. Then you have B, it's another run. And C, then another run. Okay, so you compute how many runs you have in this reshuffled version of your string. And then it turns out, and it's not difficult to see, that if the 8k period is at most k, then after this reshuffling, the number of runs will be at most 9k. Why is it so? So think again about the definition of an 8k period. You take your string and you shift it by L, which is most k, and then you have at most 8k mismatches. So when you think about position I plus 8k, I plus 16k, and so on and so forth, whenever you have a mismatch, then the character at position I and I plus 8k will be different. Yeah, that's a mismatch for this notion of being 8k periodic. Yeah, it's a position I, so that the character at position I and at position I plus 8k are different. But such two characters will belong to one progression in this presentation. So they'll be next to each other. Yeah? So they will contribute, they will create a new run. So a mismatch creates a new run, and I wrote 9k instead of 8k because you also have the, so you write down those characters for starting position 1, 2, 3, and you might get a new run at the starting of the next part of the string. Yeah? Okay, makes some sense? So the number of runs in this presentation is small if your string is periodic, but you know that it is periodic. So you can take your string, reshuffle it, and you get something with a very compact representation, very small, O of k. Yeah? So you think about it being much smaller than m. Okay, makes some sense? So that's about the pattern. So now, what do you know about the text? Well, you don't know anything. You can repeat the same procedure for the text. You can reshuffle it using the same reasoning. But now you don't really know how many runs you have in this presentation because you just don't know. But it turns out that when you think about what's happening, recall that we assume that the length of the text is at most 2m, right? We split into blocks. So now when you think about two such blocks, so you think about such occurrences of the pattern. So that's the left part of the text and the right part of the text. So you can take the left part of the text and you can isolate the longest suffix such that the number of runs in this reshuffled representation of the suffix is at most O of k. So what I'm saying is that some crazy things could happen in the beginning here and at the end. But if you have at least one occurrence, then a suffix here and a prefix here, they will compress very nicely under this run length encoding because you have an occurrence with at most k mismatches. Okay, so the text doesn't have to have this nice structure, but you can always truncate it to something shorter, which contains all possible occurrences and which compresses well under this run length encoding. And that you can do efficiently, I mean, in linear time. Okay, so the text doesn't have to be that nice, but you can always truncate it and reduce the general case to the one where text compresses well. Okay, and now your life is beautiful because you have a pattern and a text, and they both, when you look at those L encodings, those reshuffled versions, they consist of only O of k runs. So they compress very, very well under run length encoding, okay, when you reshuffle them. And then actually when you think about this reshuffling, you can reduce this question to pattern matching when the text and the pattern are given in run length encoded version, just run length compressed version of pattern matching. So the input comes in a compressed form. Yeah. So here you have to think about this L encoding, and yeah, because here I'm only saying that the L encoding is small, but you want to kind of work with this encoding, you can do that when you work a little bit. And then you get an instance of this run length encoding pattern matching, and people look at such questions a lot for different compression methods. In particular, they thought about run length encoded strings, what you can do efficiently for such inputs, okay? But there is a bad news, and that's the second time I'm mentioning conditional lower band. So when you have an instance of pattern matching in run length encoded input, so the pattern and the text, they consist of k runs. Yeah, there are k runs in the pattern and k runs in the text. It requires quadratic time, assuming the three-sum conjecture. So that doesn't give you that much. Now you can figure out what's the complexity that you would get from that. It's not what I promised yet, but it will give you something, okay? But there is also good news. The good news is that you not only know that your pattern and the text compress well, you also know that they're of length at most m. So there are two parameters, k and m. And this reduction from three-sum, it creates instances when the pattern is long. It compresses well, but it's long. Because in three-sum, you need the universe to be large enough, right? I mean, quadratic or cubic, I don't remember. Okay, so there is a good news. And now it turns out that you can again use this simple trick with partitioning the characters into heavy and light. Yeah, so that's the second case of the whole algorithm. And again, we have two cases in the second case of it. Okay, so now the definition of heavy and light is a little bit different. So now your pattern consists of runs. So you say that a character is heavy when it occurs in at least s runs. So you don't count how many times it occurs in the pattern. It counts how many runs contain this character. Okay, so when you have a run A, it counts as one for A. Okay, so you have such a definition. And when you have heavy character, you just uncompress and you plug in FFT. You don't do anything smart. And for the light characters, you work with this run length encoded version. So you have to design some algorithm for the run length encoded strings. I'm not going to show it to you, but it's not very difficult. I mean, you have to play a little bit with this run length encodings. And it turns out that when you have very few runs with a character, so it's essentially the same reasoning as we had before, just a little bit pushed a little bit further. Yeah? When something occurs a few times, you don't need to spend a lot of time for those occurrences. Here it's a little bit different, but the idea is the same. So you then plug it in, and you get that the overall complexity is k times root m for each such instance of pattern matching of pattern of length m, and the text is also of length m, 2m. So as the input, you usually get a text of length n, so you have to cut it into fragments. You have n over m of them, and then you multiply that by this complexity, and you get what I promised in the very beginning. Okay, and I think I should finish. So the last slide is that you can actually tweak the reduction that I showed you from the matrix multiplication to show that this is, again, optimal in the same sense of being optimal, which is maybe not a good sense. So if you can beat this complexity by polynomial factor, you get a better algorithm for matrix multiplication. So the only change is that you, instead of square matrices, you need to work with rectangular matrices. So you have to change that, and then the reduction is essentially the same. You have to put more special characters to make it all work, but the idea is the same. Yeah. So again, to improve this complexity, you either have to plug in a better matrix multiplication algorithm, or I don't know what else, but it would be very cool to have it. Okay, so that's it. I guess I lost you a little bit in the end, but maybe you got the idea at least what's this trick with partitioning into heavy and light characters. It's very common. I will try to put one problem on the problem set so that you can see how it works in a slightly different setting. And this first approximation algorithm, I think it's very beautiful. It's very simple and very beautiful. Okay, so if there are questions, then...
Is our algorithm false positive or false negative? It's randomized.
That's a good question. I'm not sure. I'm not sure at the moment. I'm not sure. In some cases, it works in both directions. I mean, the errors is in both directions. I think it might be both of them. At least I don't see immediately why it would be just one of them. So the whole analysis was just assuming everything is correct, so I think it might be both of them. For deterministic, it's not known how to do anything better. No more questions?